It's going to be extremely important for us to not only convert equations into matrix form, but also take matrices and convert them back into equation form. So as long as we receive a matrix and we're told that it represents a system, that should be pretty straightforward to do. In other words, assume that these columns are going to represent the coefficients of two variables. Now, x and y might be natural to want to use, and that's fine, but you can call them whatever you want if the names aren't given. You can call them m and n, you can call them p and q, you can call them x1 and x2. A lot of times that's how we label things with subscripts, but I'm going to go ahead and use x and y here. Again, they're just names, so it doesn't really matter what you call them. And then, of course, if we assume that this represents a system of equations, we know that those are the constants. So this would be the system 1x plus 2y equals 5, and 5x plus 6y equals 8. Just like that, we know exactly what the system of equations are that are represented in that matrix. In the second one, I think I'll just go ahead and refer to the variables as x1 and x2 for no other reason than just to convince you that they're just names, they're just labels. And once again, here I have the constants. So this equation reads 1x1 plus 0x2 equals 3. Now, if you used x and y, that's fine. And the second equation reads 0x1 plus 1x2 equals 8. Now, if you notice in the first equation, this really reads x1 equals 3. And the second equation really reads x2 equals 8 in their simplest form. So this system of equations that's represented here actually represents the solution equations have in common. Maybe there were two equations that didn't look like this, but after going through some algebraic process, we were able to arrive at the fact that x1 is 3 and x2 is 8. In this third example here, we have 3 equations. We have 3 rows, so that's going to be 3 equations. And once again, we'll have to assume that the variables there are 3 variables followed by constants. Again, we could use x1, x2, x3. I'm just going to go with x, y, z. And the first equation would read 1x plus 0y plus 0z equals 2. Second one would be 0x plus 1y plus 0z equals 3. And the third equation reads 0x plus 1y plus 0y 5. And just like in the second example, right, if there are 0 coefficients except for one of them, well, that actually tells us that x is equal to 2. And the second equation really just tells us that y is equal to 3. And the third equation tells us that z is equal to. So once again, whenever we read this, it gives us some valuable information. It doesn't just tell us equations. A lot of times, we can implement some sort of procedure to work on the matrix, operate on it, to get it into one of these two forms, like this guy or this guy. These are what we call reduced row echelon form. We'll mention this in a second. Well, then we can actually just read off the equations, which will represent solutions to our system. Now, we will say that a system that has n equations and n variables will have, so in other words, 2 equations, 2 variables, 3 equations, 3 variables. In these situations, they will have exactly one solution whenever we can get it into a form where each row has only one non-zero variable coefficient. Okay, notice that like in the first row, there's only one non-zero coefficient. The other one is a 0. In the second row, same thing. Coefficients is non-zero. The other one is 0. I'm not talking about the constants at all here. The constants are constants. It has nothing to do with coefficients. And then in the third example here, we have a 1, 0, 0. So that again is a one non-zero value and then other zeros. 0, 1, 0, 0, 0, 1. Having these ones along the diagonal like this and then zeros everywhere else, this is what we call reduced row echelon form. Will it always look like this? No, it'll only look like this if there are exactly the same number of equations as variables and there's exactly one solution. We'll learn more about other forms later on. So system with any, so this is called reduced row echelon form. So the question is, if we start off with a matrix, like say this one over here, 1, 2, 5, 5, 6, 8. I'm going to pick on that one for a moment. 1, 2, 5, 5, 6, 8. And if I want to get it into that form, that reduced row echelon form, then remember that my goal is to make it look like this. I would want a 1 there, I would want a 0 there, I would want a 0 there, and I would want a 1 there, so that this equation reads, and then these will obviously change, right? Because I'm going to have to do the same thing to all the values. 1x plus 0y equals some number, 0x plus 1y equals some other number, right? So that's what I want it to look like. The question is, well, first of all, I already have a 1 there, and that's good, right? If I didn't have a 1 there, if that were, say, if that number, let's say, was a 2, and to make this easier, I'm going to make this number 50 right there. Well, in order to make this 2 into a 1, and that's going to be my first task, as we'll learn in the next portion, what I can do is I can do one of 3 things. I can interchange any 2 rows that I want. I can, in other words, swap them. Well, why could we do that? Why were we allowed to do that with a matrix? Well, remember, each row just represents an equation. So whether I say 2x plus 2y equals 50, and then 5x plus 6y equals 8, that's the same thing as saying 5x plus 6y equals 8, and 2x plus 2y equals 50, is it not? I mean, they're the same equations, I've just said them in a different order. They still have the same solution. Sometimes it's helpful to swap equations, like let's say you already had a 1 down here. Well, it'd be convenient to have that 1 up in the top left. So that's an operation that we can do. We could also do this. We could scale a row by any non-zero constant. Scale just means multiply a row by any non-zero number. The reason I want it to be non-zero is if I multiply a row by 0, game over. We just zeroed everything out. But if you think about why this is possible, remember, if this first equation, the way I have it written now, is 2x plus 2y equals 50, and I want that coefficient of x to be a 1, what I can do is I can multiply both sides by 1/2. I'm going to write it like this, right? And then I have to do the same thing to both sides. So 1/2 1/2 of 2 is 1, and then 1/2 of 50 is 25. So if I take 1/2 times row 1, what that will leave me with is 1, 1, 25. And then the second row, I'm not going to change. I want to just do one thing at a time, otherwise it just becomes confusing. Now, another thing I can do is I can add a multiple of any row to another row. Okay, that would be just like adding 2 equations together. You probably agree that I could add 2x plus 2y equals 50 straight down with 5x plus 6y equals 8. Right? Because if you think about the balance of an equation, right? If the equation is balanced, that means the 2 sides have the same weight. So if I take this, and that's the same as this, and 5x plus 6y is the same weight as 8, that's also a balanced equation, then if I take what I have on, let's just say, here I have bigger, different size boxes, but the 2 sides have the same weight on them. If I add together these 2 weights and I add together these 2 weights, where this is our equal sign, well, then the 2 sides are still balanced, right? Furthermore, if I scale an equation, that's valid, it still keeps the balance. If I double the weight on both sides of, say, or half the weight of both sides on this equation, then I can still add it to the second equation as long as I haven't messed up the balance on the first equation. Okay, so what I'm saying here, and we'll learn how to execute this strategy. Let's say I want this to become a 0. How do I get that to become a 0? Well, I can swap rows. That's not going to help. I can scale the row by 0, but that's not going to help because we don't want to zero everything out. But I can take -5 times row 1 and add it to row 2. What will that do? Well, -5 times 1, okay, so first of all, I'm not changing the first row. I am just adding some multiple of one row to another. -5 times 1 plus 5 is 0. -5 times 1 is -5 plus 6 is positive 1. Negative 5 times 25 is negative 125. Negative 125 plus 8, if I'm doing my math correctly here, is negative 117. And so you can see operations, if we use them appropriately, sometimes I'll need to scale a row to get the right coefficient, basically turning something into a 1 whenever I need to. And then I'll have to use row operation 3 here, adding some multiple of one row to another, if I want to take something that is non-zero and turn it into a 0. Because again, I can't scale the row by 0, otherwise I clear the whole row and all of the values become relatively worthless. So this is where we'll go with next is, okay, how do we implement these 3 steps to get something that starts off like this, 2, 2, 5, 6, and get it into the form 1, 0, 0, 1, reduced row echelon form.